In today's video we are going to evaluate this integral, which is the integral of the square root of tan of x from 0 to pi over 2. You'll notice that we're allowed to do it in terms of it being completely real, i.e. not having to deal with any complex numbers here, because tan of x is positive from 0 to pi over 2, so taking the square root is perfectly fine. Okay, now there's a wide variety of ways in which you can evaluate this integral. I'm going to be employing the beta function, and by natural extension the gamma function, as a way of evaluating it. So the first part is if we take tan of x in terms of its definition, sine of x over cos of x, we see that therefore the square root of tan of x is the square root of sine of x over cos of x, which is the square root of sine of x over the square root of cos of x, which if we represent it in terms of powers is sine to the power of 1/2, cos to the power of negative 1/2, the negative 1/2 because it's obviously 1 over. So what we're going to do is we're just going to plug that into this integral. Okay, and we see the integral that we had, the integral from 0 to pi over 2 of square root of x, becomes the integral from 0 to pi over 2 of sine of 1/2 x cos of negative 1/2 of x dx. Okay, so from here we're now going to go into the beta function. So the beta function is a very common special function, and actually you'll see that I've actually made a mild mistake here. This should be a dt, so just so people are aware. If anyone wants to learn more about the beta function, it's something that I highly recommend. I will have a link in the description. But what we see here is just the Wikipedia page. There's some fantastic information on it, and we're going to be coming back and forth to this to get a few identities. So this is the general definition of the beta function. So for any two complex numbers a and b, whereby the real part of a and b is greater than 1, beta of a comma b is the integral from 0 to 1 of t to the power of a minus 1, 1 minus t to the power of b minus 1, and again that should be dt. Now this, if we make a simple substitution, can be represented in this form using sine of x and cos of x. Once again, we see that for anyone who wants to see, if we go to the Wikipedia page, we can see that we have this definition here. If anyone is interested in seeing how to go from this, the initial definition, to which is what we have here, down to here, please let me know and I can put that into another video. Okay, great. So we now know that this beta function here can be represented into this form. And if we have a look at what we have here, obviously this is taking this form. We've just got this 2 out the front. So if I wanted to just have something with, sine to the power of something, cos to the power of something in the integrand, I just need to divide by 2, and that's what we see over here. The integral from 0 to pi over 2, sine to the 2a minus 1 of x, cos to the 2b minus 1 of x dx is equal to 1/2 of beta of a comma b. And so what we want to do then is we now want to solve, okay, well then what is the value of a and b that matches up with what we have here? And so that's what we see in the next step. So if I have 2a minus 1 here is equal to 1/2, what is the value of a? Obviously just some very simple algebra. We find a is equal to 3 over 4. Similarly, we want to have for 2b minus 1 equals to negative 1/2, which is what we have here. Again, some simple algebra shows that this is equal to 1/4. So what we've got here is we now know that this integral here, which remember is another form, exact same integral as what we're looking to solve, can be represented by the beta function, where a is equal to 3 over 4, b is equal to 1 over 4. So we'll see that in the next step. So I, the integral from which is the integral from 0 to pi over 2 the square root of x, which we showed is equal to this, is equal to 1/2 beta 3 over 4, 1 over 4. Now, technically, that's a solution. I mean, if we want to express it in terms of the beta function alone, that is the solution. What we always try to do, obviously, whenever we're approaching integrals is if we can express it in terms of an elementary value, as opposed to having to rely on a special function, we will. And in this case, we can. And so quite often when I'm working with the beta function and I get to something of this form, my immediate thought is, okay, let's express this in terms of the gamma function. Now, the nice thing is that the beta function is directly related to the gamma function, and there is a very simple relationship that combines the two. So once again, we'll go to Wikipedia and I will show you. If anyone would like to see the derivation of this, once again, please advise. and I will put together a video that shows the derivation of this. So where are we? Okay. Sorry. Here, so we see the relationship between the beta function and the gamma function. Okay. So with the derivation that we have here, we see that gamma of x, gamma of y is equal to gamma of x plus y, beta of x, comma y. So obviously then, if I want to have this isolated, I just divide it through onto this side, and I have beta of x comma y is equal to gamma of x, gamma of y, divided by gamma of x plus y. So that's the relationship between the two. So that's what we have here. So now that knowing that we have this, we're just going to apply to the situation that we have. So I, which equals 1/2 of beta 3/4, comma 1/4 is equal to 1/2. So just leaving that out the front and just applying this rule, gamma of A, gamma of B over gamma of A plus B. So we've got gamma of A, which is gamma of 3/4, gamma of B, which is gamma of 1/4, divided by gamma of A plus B, 3/4 plus 1, which is equal to 1/2. Remember, that's just out the front. Gamma of 3/4, gamma of 1/4, which is gamma of 1. And gamma of 1, for anyone who isn't familiar with the gamma function, I highly recommend that you spend some time looking into that, but it's essentially an extension of the standard factorial that we're used to. So, n factorial, which is n times n minus 1 times n minus 2, etc., and going down. What if we want to extend that so that we don't have to include just whole numbers? And that's what the gamma function is. So here I'll put a link to, but the gamma function is an amazing function that crops up in so many integrals and so many applications. I absolutely love it, and in the videos that will be producing, in tutorial videos, this will come up a lot. Okay, so let's go back. And so now we find that we have taken our integral, which previously was in the form of the beta function, and we've now expressed it in terms of the gamma function. Now you might wonder why I've expressed this following line, and that will come about in the next line. But obviously this is a situation here where gamma of 3/4, well, 3/4 is just equal to 1 minus 1/4. So we've got this situation of 1 minus t times by gamma of t. And I've done that very deliberately because there's a special relationship that comes about from this, where we can take this form and express it in terms of the sine function. And what's beautiful about that is that I'm going from a special function, which is gamma, to an elementary function, which is sine. So as I said, our goal is to always try and express it in the most elementary form possible. Sometimes we can't, and that's perfectly fine. But where we can, we try to. Okay. So there's a really, really famous function. Sorry, these two shouldn't have come up at the same time. Let's just look at this line. And this comes about from what's known as Euler's reflection formula. I have a link once again, which says gamma of 1 minus t times gamma of t is equal to pi divided by sine of pi t. Now this holds for any complex number t where t isn't an integer. So once again, if we have a look within here, I'll have the link here, you'll see that there are many different forms of the Euler's reflection formula, but a very, very famous one is the one that involves the gamma function, which is what we've got here. And you'll see here, exact same formula we got, I've just got it the other way around. Obviously, multiplication is commutative, so it's no problem, but z cannot be an integer. Now, in this case, coming back, we have a look, is z an integer? Well, t in our case. No, well, t is a fraction, 1/4, that's not an integer, so we can apply this. So, again, I, which equals 1/2 of gamma of, remember it was 3/4, but we express it as 1 minus 1/4, times by gamma of 1/4 is equal to 1/2. This is just that 1/2 at the front. Pi over sine of pi t. So we've got sine of 3/4 pi. Oh my goodness, I have made a mistake here. That should be 1/4 pi. My apologies for that. I will correct it in the link that I will provide for download. And the nice thing about that is sine of pi over 4 is actually something that's very, very simple. We can just use, what do they call them, the identity triangles for that. And it's just equal to 1 over the square root of 2. So we have 1/2 times by pi over, remember, my apologies, this should be sine of pi of 1/4 pi, or pi over 4, which is equal to this, which is equal, and, pi divided by 1 over the square root of 2. Obviously, if you divide by a fraction, we just invert it. So we've got square root of 2 over 2 times by pi, which is just equal to pi over the square root of 2. And so, as a consequence, we find that our integral I, which equals the integral from 0 to pi over 2 of the square root of tan of x dx, is equal to pi over the square root of 2. So although we've had to use some very special identities, we've taken it from the beta function, which is a special function, and then we've converted it into the gamma function, which is another special function, but it's I wouldn't say it's better to represent it in that form, but it's generally classically done. There's obviously, if we have the beta function and the beta function is just a composition of the gamma function, then as much as it is nice to use the beta function, if we don't need to use it, i.e. we can express it in terms of another function, then why double up with introducing a new function or using that new function? Not to say that the beta shouldn't be looked at, it's an incredibly important function, but after you've got it into this form, put it into the gamma. That way you're only dealing with one function instead of two functions. But anyway, going through that, we then employ Euler's reflection formula, and then, as I said, there has been a slight mistake there. That should be 1 over 4, and we get that our result is pi over square root of 2. Pi is obviously an elementary, well, it's a transcendental number, but these are known values. So we've expressed the result in terms of an elementary form, which is what we were trying to achieve. So, okay, so this is my first video. You'll see here that instead of actually using like a pen and paper, I have just used some latex instead. That's because I did recently purchase an iPad, but then I found out that you have to spend a ridiculous amount of money for the pen as well. So I'm trialing this first, and I'm going to see the feedback that I get on this video. If people are happy with this format, I'm going to continue with this format as well. Okay, so I really hope you've enjoyed this video. Please let me know what you think, and if you would like, subscribe. And I will be releasing videos on a very regular basis. I would say I'm hoping at least 3 a week, and I will be taking requests. So if you have requests, please send them through to me, or either post a comment on the page or send me through a private message. And if I'm able to do the integral, I'll be more than happy to put up a video for it. And that's something that the page will take, or the channel I should say should take, is that there's no actual formal structure that's going to be taken. It's just, I really like integration. And I love working on tricky integration, square root of 10 of x. It seems like this really difficult one to approach. And so it will just be sort of random assortments. But I will also hope to cover some more generalized methods where I go through, instead of, as we have here, needing to know a few tricks of, well, how did I know to use those tricks? Well, I know to use these tricks because I've been working with these integrals for a very long time. So as soon as I saw 10 of x, I'm like, oh, right, okay, well, if this is going between 0 and pi over 2, I know that the beta function can be represented into this form, therefore I'm going to use that. So, it's about picking up on those patterns as we go along. Anyway, I'm going on. As I said, I really hope you enjoy. Please hit like, and if you want to subscribe, please subscribe. Otherwise, have a great one. Bye.